So we will now write the force balance equations for idealized translation translational system or translatory elements. Translatory elements. Okay. So therefore, in this section, now we will take individual element, and for that we are going to write the force balance equation. So in that, so first we will consider the mass element. Mass. Okay. So the mass is now represented like this. So the entire mass is assumed to be concentrated at one point. So assume that here the force F is applied, and here it is the reference, and because of the applied force, the mass gets displaced by x, or the displacement experienced by the mass considered as x. So here m represents the mass, f represents the applied force, and x represents the displacement. Okay, so therefore now we know that this f applied force is proportional to acceleration. Okay, so because when the force is applied, the mass gets accelerated, or you can write f is proportional to dv by dt, that is the rate of change of velocity. Okay, or you can write f is proportional to d by dt of velocity is nothing but it is dx by dt, rate of change of displacement. Or you can write f is equal to m into d square x by dt square. Okay, so this represents the force balance equation for mass element. Okay, so here how to develop this? So we consider a mass, F is a force applied to it, and x is a displacement. Okay, so therefore the applied force, for the applied force, an opposing force will be given by the mass. Okay, and this F will be proportional to the acceleration of the body. Okay, and then F will be again proportional to what? Acceleration is nothing but d by dt, rate of change of this velocity v. Now we will substitute for v. Okay, so v is nothing but again rate of change of displacement. Okay, so therefore substitute for v, therefore we get f proportional to d square x by dt square, or f equal to m into d square x by dt square. So therefore here, because the displacement x it depends on the mass of the body also. Okay, so for the same applied force, okay, so a lighter mass may move to a maximum distance. Its displacement may be more when compared to a heavy mass. Okay, so even though same force is applied, okay, so the amount of displacements it gets will be less. So therefore the applied force, mass and displacement, okay, so they are related by this equation, and this is called as a force balance equation for the mass element. So next, we'll take the So our second element will be damper or friction element. Damper or friction element. Okay. So therefore the representation of that will be, this is the symbol to represent the damper or the friction in a mechanical system, and here I am writing B. This actually represents piston inside this particular cylinder. So this symbol shows the friction. Okay, so in an entire mechanical system, wherever you find this particular symbol, so this shows that particular part is experiencing the friction. Okay, so now here also when F is applied, so it gets displaced by X. Okay, so now this friction is associated with the mass also. So assume that whenever you are applying some certain force to the mass, so then the mass gets displayed. At the same time, the mass will also experience the certain amount of friction also. So therefore that friction is nothing but this representation. Okay, so therefore now uh, this particular damper element, it offers an opposing force. Okay, so for the applied force F, and this force F will be proportional to V, velocity. Okay, so therefore this F will be proportional to dx by dt. Okay, because V is equal to dx by dt, rate of change of displacement, or F is equal to B into dx divided by dt. Okay, so this is the representation for the friction element. So therefore for the friction, F, that is applied force, is related to the constant B as well as the displacement x. So as more force is applied, then mass will be displaced more, and because of that experienced force, it may experience a greater friction also. So now when dashpot element so has displacement at both ends. Okay, now this in this example what we have shown, the damper element has a displacement only at the one end. Okay, so if uh, the same damper element, if it experiences, okay, the force at uh, both ends or displacement at both ends, so then how to write the force balance equation? So for that, let us uh, draw again the representation, that is D. So here applied force F is there. Okay. Then assume that the two ends have the displacement like this. Okay. So this end is associated with displacement x1, whereas this end experiences a different displacement x2. Okay, so therefore now the two ends of the dashboard are under different displacement. So therefore now whatever this F is there, okay, so this will be proportional to V1 minus V2, because now the two ends are not at the, they may not be at the same displacement. Okay, so they may be at the different displacements also, but anyway F will be proportional to V1 minus V2, difference of velocities, or F is proportional to dx1 by dt minus dx2 by dt. Okay, or F is equal to this b into dx1 by dt minus dx2 by dt. So this is the force balance equation whenever uh, the damper element experiences two different displacements at both the ends. So still we have another element, that is the spring element. So for the spring element, the representation will be third one, right? Spring element. Right? So for the spring element, you can write the spring like this. This is the reference and applied force F here. So this is the spring constant K, and this end experiences the displacement X. Displacement X. Okay. So therefore now consider an ideal elastic element. Okay, so it is nothing but this actually what it represents is elasticity of the body. That's all. Okay. So previously we have seen the friction. What was that friction actually? It is actually experienced by that mass. Okay. So similarly here the spring represents elasticity of the body. Okay. So now assume that as it is an idealized spring, it is associated with a negligible mass and negligible friction. That is, both M and B are zero for this. It is purely a spring element, ideal spring element which is having no mass and no friction. Now let us consider that the force F is applied to it. So now because of this, when you apply a force on the spring, okay, so the spring is going to offer an opposite force. Okay, so now that will be proportional to displacement of the spring or displacement of the body, you can imagine in general. So therefore, whenever you apply F, so it will be proportional to X. Okay, the spring will offer an opposing force which will be proportional to the displacement of the body, or F is equal to K into X, where K is the spring constant. Okay, so with what speed the spring comes back when you release the force, that depends on the spring material also. Okay, so now that constant is represented by K here. Okay. So now this is the relation between force K and X when only one end of the spring is experiencing the force. But if the two ends of a spring are experiencing two different displacements, so then we need to again write another force balance equation. So under that condition, consider that we have again the spring K. Okay, so then this end is displaced by x1 amount, this end is displaced by x2 amount. Okay, under the applied force. So now in this case, as two ends have different displacements, so here we will write F will be proportional to x1 minus x2. That is what we can say, the opposing force will be proportional to differential displacement. Okay, so this is called as what? Differential displacement. Okay, or F is equal to K into x1 minus x2. So this is what is the uh, force balance equation for the spring element which is having two different displacements at the two ends. Okay. So therefore, in case of mechanical systems, so now we have what discussed three ideal elements. Okay, what are those? First one is the mass element, second one is the damper element, and third one is the spring element. Okay, so therefore what are the different symbols that we are using in mechanical translational systems? So symbols list of symbols uh, used in mechanical translation mechanical translational system. So in translational system, whenever force is applied, the body gets linearly displaced. That's all. Okay, in rotary systems, the displacement will be different. It will be in a rotational form. Okay, so later that we will discuss. So this is nothing but the list concerned with the symbols used in mechanical translational systems. So therefore, first what we have is the displacement x. Okay. The first symbol we are using is x. X we used here to represent the displacement. Displacement. And now this capital V here, which is nothing but dx by dt. So this represents the velocity. Velocity. Velocity of what? Velocity of the body which is under force. So F here represents the applied force. Applied force. And capital M here, it represents the mass in kg. Okay, and here the symbol B or B is used to represent the friction constant, or it is also known as the friction coefficient. Friction coefficient. And lastly we have K. K is known as the spring constant, or it represents the stiffness of the spring. It represents stiffness of the spring. Okay, so for mechanical translational system, we have x representing the displacement, v representing the velocity, f represents the applied force, then m represents the mass, b represents the friction coefficient, and then k represents the stiffness. So we will use these notations throughout this module to further analyze the systems and draw the analogous systems. So therefore, to just summarize the different elements. So for a mass element, okay. So for a mass element, what is our force balance equation? F will be equal to m into d square x by dt square. Okay. Similarly, in case of damper element, so in case of damper element, we have uh, two equations. Okay. So damper or friction. So now onwards we will be using this friction term more repeatedly. Okay. So one equation is F equal to B into dx by dt. So this is when only one side of the friction is experiencing the displacement. There is only one displacement, only x is there. Okay. So next we have one more equation also, that is F will be equal to B into dx 1 by dt, okay, minus dx2 by dt whenever the damper element has displacement at both ends, x1 and x2, as shown here, as shown in the picture. Okay. So then next we have the last element, that is spring. So this represents what? Elasticity present in the mechanical system. So for this also we have two equations. One is F is equal to k into x, and the second equation is F equal to k into x1 minus x2. Okay. So when we are using this equation, when the spring experiences only one displacement at one end. So this equation is used whenever spring is displaced at both the ends, x1 and x2. So this is the spring constant k. Okay. So in mechanical systems, both are possible. So an element may be displaced at only one end, or it may be displaced at both the ends also. Okay. So this is a summary of translational systems. In the next session, we will consider mechanical rotational systems.